Hello everyone, welcome back. This is your Professor Yao Xie again. Today we'll talk about clustering, which is a basic unsupervised learning algorithm, meaning that we don't have any label for our data points. So to start with a motivating example, we talk about this briefly during introduction. Suppose you have a pretty large image database and you collect tons of images, and these images are about different subjects, for example, about the sea, about flowers, sunset, and so on. And without any label about these images, the question is, can we group these pictures into clusters based on their similarity? As you can see clearly, for example, these images about the beach have similar color and similar shapes about the seashore and so on. So clearly there's some similarities between the images. Okay, so based on that, the goal of clustering is to divide the object into groups, and hopefully the object within the group are more similar than those across different groups. Here's another module example, clustering the handwritten digits. This is a very classical example in machine learning, and this data is the handwritten digits called MNIST dataset. And this dataset is collected from the USPS mails where people write zip code on the cover of the envelope, and we take scan pictures of their handwritten digits and do pre-processing and extracting these handwritten digits by different people. As you can see, of course, the people have different ways of writing digits. There are different ways of writing 7, slightly different, although you can still recognize this is 7, but it looks sort of different. Okay, and so the question here is, based on these images, if you put them together, can we find clusters of images? For example, a cluster of images all about 7, a cluster of images all about 1 and 2. Can we find an algorithm to perform this task automatically based on the similarities of these little images? And in fact, in this class, we will do multiple exercises in our homeworks based on this this image data set. This is one of the most simpler and highly widely used data sets for testing machine learning algorithms because it's fairly simple and has been pretty well pre-processed so you can extracting features from these images. So how do we represent these images? We'll define features from these images. So if you look at each tiny little picture in here, it actually consists of these pixels. Okay, and so, for example, in this binary image, and we could say if there is no stroke, it's a 0. If there's a stroke, then it is a 1. Okay, so by representing this image by pixels, and this is going to give us a matrix, a square, and the size of the matrix is the number of pixels along the rows and columns, and the entries in this matrix are going to be zeros and ones. And one thing we typically do is we will vectorize this matrix, meaning that we're going to extract the columns of this matrix and stacking them together to form a pretty long vector. Okay, this is called the vectorize matrix. After vectorizing the matrix, we end up having a pretty long vector. This vector represents its image. And we're going to define this vector as dimension n. N is the number of pixels in the image. This notation we're going to see many times in the class representing this is a n-dimensional vector in the Euclidean space. The values of each entry is a real value. Okay, so basically you end up having a bunch of zeros and ones after you represent each little image by the vectorized pixels. Okay, and so how do we approach this problem? Before the clustering, each data point now is this little image. It's represented using this long vector. Okay, now we're going to talk about where do these vectors live. In linear algebra, okay, these vectors define a vector space. Okay, these images live in a vector space. And so you can imagine, right, this vector space is going to be pretty high dimensional. As we see earlier, it's n-dimensional. For example, these little images consist of, I think, 9 rows and 9 columns roughly. So it's going to be 90, about roughly 90 pixels or something, right? So, but you can imagine they live in this high dimensional space, and then each data points here, right, representing one image. I draw this in a 2-dimension, but you can imagine this is actually happening in a very high dimensional space. So before clustering, I don't know what these images are. They could be any of these 10 digits from 0 to 9. But if you look at where they live in this high dimensional space, the digits that are similar to each other will be pretty close to each other in this high dimensional space. So based on that, can we cluster and divide these data points into groups such that the data points belong to the same cluster will highly likely to be the same cluster. So that's the idea. Okay, so the algorithm we described next will perform this task. So to start with, we will assuming these so-called centroids. Okay, in this example, we're going to start to choose 3 centroids. And why 3? For example, you believe that there are roughly 3 clusters in your data, and so how to choose the number of clusters is also a question to your parameter we will tune in this algorithm. Okay, so once you choose the centroid, then we can assign the data points to the centroids based on how close they are to the centroids. So, for example, if you define Euclidean distance, then we can find out the data points close to each of the centroids and give it a label this time. So these data points are close to this first centroids, and they're all colored in green as the data points belong to this particular cluster. And these ones, based on the calculations, these are the points closest to this particular centroids, and these are close to this particular centroids. Okay, and so after this, you have assigned a group to each of the data points to each of the centroids. Okay, and so once you have assigned the group to each of the for each of the samples, you realize that this initially chosen centroid in these locations may not be the best locations. And so based on that, we can adjust the centers, adjust the centroids based on the assignment. That is simply done by performing the average of the data points, and the average of the data points in the same group is going to be assigned as a new centroid. Okay, so this very simple idea becomes our first algorithm called the k-means algorithm. So I'm going to describe this algorithm below using pseudocode. As you can see here, we're going to start to introduce some mathematical notations. Given m data points, here this m represents the number of data points. So this is going to be the convention in this class throughout the whole class. M is going to denote the number of data points. And each of the data points is an n-dimensional vector. Remember, that's the number of pixels for each image in this example. And one convention we also have is we're going to put the index for the sample as a superscript to the x. And with the understanding that any of these xi's is a n-dimensional vector, representing a vectorized image. And next is we're going to find the k-cluster centers. These are the centroids that we were talking about just now, these k-cluster centers. And k is the number of clusters, and this k have to be pre-specified. And based on that, we will find an assignment of data point to one particular cluster. And you can imagine this assignment is a function. This function is pi. Its argument is I, and then its output is one of the integer values between 1 and k. And so this basically tells you the ith data point belong to one of these clusters. Okay, so what is this algorithm? Here is a formal description of k-means. And we will first have an initialization. As you can see, a lot of the algorithm we talk about this class will have some kind of initialization. Here we will initialize the centroids randomly. In your homework, you'll practice implementing the k-means yourself, and you will see how to randomly assign the centers. For example, you can set these as multivariate normal random vectors for each of the centroids. And then after that, we will iterate between the two steps in this algorithm. And these two steps correspond to assigning clusters for each data points, and then adjust the centers for the one cluster after we have done the assignment. So, and then you're going to do this, and then coming back, and then repeating these two steps. So if you look into each of the step in the center assignment, and the first thing is we're gonna assign a data point to a particular center using distance. And here, this notation here represents the L2 norm of a vector. And so what does it mean? This z is going to be the square root of the sum of entries of okay, here's the square. All right, so that's our usual definition of the distance in the vector space. And so this is a squared L2 norm. And so basically you find out for each data point which centroid is the closest. And then you're going to assign it to the closest centroid. So this pi I is the argument finding out the closest, meaning the smallest distance for this particular data points to that particular centroid. And after that, we're going to adjust the centers. And so once you have these pi's assign the ith data point to the particular cluster. And so you basically, this summation here, you can see this representing that finding out all the data point that has been assigned to the J's cluster. And then you will perform an average of these xi's. And then this is average, so you're going to find out how many points has been assigned to the particular cluster. And so this notation here means that we're going to count how many points has been assigned to the J's cluster. Okay, so this is nothing but performing an average of that. And that's it. So after the adjustment of the center, and you will realize it's possible that because the center is different, so the assignment of the points will be changing as well. So you will go back to the first step and reevaluate assignment of the data points, and then go to the next step to adjust the center as well. You keep doing these two steps until there's no further change. So while there's no change in this cluster centers, okay? And then this is the termination of your algorithm. Okay, so let's see what's going to happen after we run this algorithm iteratively. Again, we use this very simple example. This is what it looks like to start with. We have 3 randomly chosen centroids, and then we will assign the data points to the closest centroids, and then these points in green has been assigned to the first centroid, and otherwise second and third, and so on. So essentially, by this assignment, we are performing a partition of the space. Okay, so this partition of the space is formed by finding the closest distance of the data points to its centroid. Okay, and after the assignment, the next step is to adjust the centroids, and if you basically performing the average of these points that has been assigned to the first group, and then if you perform that, you can see this tends to drag the initialized centroids into some position here, and this might be adjusted to here, and so on. Okay, so after the first and assignment and adjusting centroid, this is what's going to happen. And then from here, you can do the same thing again, finding out the assignment, and based on the new centroids, as you can see, some points the assignment will be different. For example, you will see, let's see the next iteration, and then based on the new assignment, you will do adjustment of the center again and iterate until there's no further change. So you can flip through this animation and you will see what's really happening here to get the idea until no further change is happening to the centroids. Okay, so we have to describe the algorithm and see the steps. And here is the time for you to think about what are possible results can happen and possible properties of this algorithm. First question, will different initialization leads to different result? Yes, no, or sometimes? And second question is, will the algorithm always stop after some iterations? Okay? All right, for the first question, yes. For different initialization, you have different results. And for the second question, yes. Okay? And we'll explain the answer to these questions in the next few slides. All right, so first of all, okay, give a little bit intuition why different initialization will lead to different results. But first of all, basically, we are solving the so-called non-convex optimization problem for the k-means. And so for non-convex optimization problem, there are many local solutions, and we only end up being one of the local solutions. It's only locally optimal. And so because of that, different starting point might lead into different local solutions. So you might not have different results based on different starting points. And the second is, yes, it will stop. The reason is after a finite number of iterations. The number is, since you have a fixed number of data points, there's only a finite numbers of ways to perform enumeration and combinations of these points to the centroids. Although it's a big number, but there's a finite number of ways. And our algorithm always try to reduce a certain metric, okay? And so after many iterations, could be many iterations, but it's going to converge. It's going to, because you keep decreasing until the point you cannot decrease further. Okay, so here is a formal statement of the k-means objective. Given m data points, we want to find k-centroids or cluster centers and find out this assignment function. And so what is our objective function? We want to minimize the average square distance from each data point to its respective cluster center. Okay, we want to minimize the overall sum of squares errors of representing these x with centroids. That's it. So as you can see, this optimization problem involves two things that we want to minimize. One is the pi, these are the assignment function, and the other is the c, the centroids. So you can see that's why we have these two steps in each iteration. We're basically adjusting the assignment function and also the centers, the centroids in this. And then the objective function, the so-called objective function, is defined as the sum of the squared L2 distance here. Okay. All right, so we have an optimization problem to solve and how easy or difficult it is to solve this. It turns out, unfortunately, this problem, if you want to solve it exactly, it is NP hard. NP, what does NP mean? It means non-polynomial. So that means if you want to solve this problem, find out the exact optimal solution. So what does it mean? If you plot the value of the objective function, so this is a total variation, this is the objective function, and then you will end up having this shape, okay? And so you can see this is the actual minimum of the objective function. That's called the global minimum. But there will be some places like a valley, and these are not as small as the global minimum, but they're also pretty small. They're pretty small, smaller than all the neighbor points. These are called local minimums, okay? And so basically this objective function is going to take this ugly shape that is pretty hard to find the global minimum. So if you end up starting from different points, you may end up having different, if you start from here and then you go down, you might be trapped in one of the local minimum and couldn't escape from there. Okay, so that's one challenge because of the non-convexity. And Because of the non-convexity, we cannot use a very simple iterative algorithm to find the exact solution. Non-convexity is causing a problem. And if you really want to find out the exact solution, because the number of ways to assign data points to a centroid is going to be k raised to the power m. So that's the number of possibilities. Why? Because for each data point, you can assign it to one of the centers. You have k centers, k centroids. So you will have k times k times k. You multiply this by m times m is the number of samples. So there are total k raised to the power m possibilities, which is a astronomical number. So that's why it's a very difficult problem. It's NP hard to solve. So because of that, we're not going to solve an exact global optimal solution. We're only going to solve a local solution, and then this heuristic algorithm end up solving this problem approximately actually gave rise to this K-means algorithm. Okay, and so the convergence, okay, we're talking about whether or not this is going to converge in finite number of steps. It actually will converge in finite number of steps. So the first thing is you can think about question, will k-mean objective function oscillate? And the answer is no. It will not oscillate. It will be monotonically decreasing. If you look at this objective function, this is the objective function. And why? Because if you think about the two steps you're doing in the iteration, they're always going to make the change only if you're going to improve, meaning reduce this objective function. If your new assignment or new centroid is not going to reduce objective function, you're not going to make the change. Because of that property, your objective function is always going to be monotonically reducing. Okay, and the second question is the minimum value of the objective function. Look at this. If you choose any c and any pi, what is the smallest possible value that your objective function could be? It's going to be 0, right? Because this function is sum of the squares numbers. The squared numbers cannot be negative. So sum them together, the smallest you can possibly have is 0. So basically, we're forming a sequence of objective function values in the equation, and then they're monotonically approaching to 0. Because of that, there is some theory in mathematical analysis guarantees that your algorithm is going to converge in finite number of steps. It's going to converge for sure. And then because you have only a finite number of combinations, which is a large number, which is k raised to the power m, it still is a finite number, so you will converge in finite number of steps. Okay, so this bullet point explains further why each iteration will decrease the objective function. Okay, so now we have a pretty good understanding of k-means. Okay, and so there's one interesting point I would like you to think about, which is how do we define similarity in the k-means algorithm? Okay, so the definition of similarity is quite subjective if you think about it. And here I give this very interesting example that I find from this website. You can check it out. And it's not English, but you can translate it if you're interested in reading more. And so these are different characters from Simpson family. As you can see, if I want to group these characters into groups, depending on your metric, you could group them differently. And for example, if I define a group as Simpson's family and school employee, and I end up having these two groups, okay? But if I define the group metric as females and males, then I will end up having different ways to group them, right? Okay, so you can see this is going to change the result of my cluster if I change what is my definition of similar and dissimilar. Here's another, I think, interesting example. A girl with curly hair and a puppy with curly fur, okay? Do you think they are similar or dissimilar? Depending on your metric. If I define the similarity as both having curly hairs and fur, and maybe their similarity is pretty high. Okay, but of course they're different. If you define them as a human versus non-human object, they're different. So another example to show you this idea. Okay, and so how do we generalize the K-means algorithm to be able to account for the general definition of similarity? Okay, so let's revisit K-means. You will see we can do this by simply choose the similarity function and the K-means algorithm. You can pick your own similarity or dissimilarity function, and then the rest of the step in K-means will be the same by finding the most similar ones as the centroids, reassign them, and so on. Okay, so again, let's look at some examples to illustrating what do I mean by different definitions for similarity functions. Okay, and so for example, how do I define a comparison or similarity between images of different sizes, right? So we talk about these MNIST handwritten digits to start with, but these images are the same size. And if I have different images, these are both about flowers, one about tulip, the other is about rose. And instead of defining them using raw pixels, I could define them differently. For example, I define the features as their color, their texture, composition, and so on. Okay, so you can see this time these features are not the values of the pixels, but they are something you can extract out of the picture. These are different features. Okay, so that's another term you're going to see many, many times, features. Okay, so this way you can define a more abstract way of representing your data. And then the object in real life, you can also define clearly features, for example, in terms of their family, their gender, the working place, their age, their preference, and so on. And so you have many different ways to define your features for Simpson's family, and this is going to end up giving you a vector. Okay, the question next is, once each data point is represented using a vector, this vector contains values of the features you have chosen. And then measure the similarity between these data points is a problem of choosing a function to measure the distance between two feature vectors, okay? And so we're gonna say, how do I define this feature vector? And for example, if you revisit the k-means, you'll realize that we actually have made the choice that this similarity function is x minus y squared, the squared altitude distance. Okay, but why do we choose that? You can totally choose it to be something else. And here, that's the point we want to generalize. And what is a good similarity function that can be used here to replace the Euclidean altitude distance square, altitude distance, sometimes called the Euclidean distance, and this is a squared altitude distance or squared Euclidean distance. So first it has to satisfy some symmetry, and so dxy is equal to dyx. And because you want to make the claim that if A looks like B and then B is the same as A, you don't want to make the argument doesn't hold, then it's kind of tricky. And the second is positive separability. So if the two objects or two data points have zero distance, this can only happen if these data points are exactly the same. Okay, so you want to define this way because you want to differentiate the object if they're truly different. Right? If you map the two objects that are different into zero distance, then that's going to cause ambiguity here. And the next one is triangle inequality. And so basically this says, if there's x and there's y and there's a z, and you will say the distance between x and y should always be smaller than the distance of xe and then the distance from z to y. Okay, so satisfy the triangle inequality. So your D satisfy these requirements is going to be a legitimate definition of similarity function. Here are some examples of similarity functions. So again, given two vectors that are n-dimensional, and the Euclidean distance or altitude distance that we have used in the k-means algorithm so far is based on this definition. The sum of the square distance of the entries And this can be generalized to the so-called Minkowski distance. And you can see instead of 2, I could define as 2 as the sum of the piece power of difference in the norm. And then you take the piece square root of that. So Euclidean distance definition is according to the p is equal to 2. And actually when you take p is equal to 1, it's called Manhattan distance. This is the sum of the absolute difference between x and y entries. And so why is it called Manhattan distance? We'll have one example illustrating here. And so by the way, if you set p is equal to infinity, then this distance is called infinity distance. That's basically the maximum absolute distance between entries in the two vectors. Here is one example illustrating the difference between these norms. And so in this example, we have the two-dimensional vector x and y. And so they form this relationship. So Euclidean distance between x and y, because of the so-called Pythagorean theorem, is going to be the distance this way in x and distance in the other coordinate squared and take the square root is going to be 5. And the Manhattan distance between the two is going to be the sum of the absolute difference between the two theta points. So in this particular direction, the difference is 4. In this direction, the difference is 3. So the sum of the difference becomes 7. The infinite distance is going to be the maximum of the distance, maximum of the difference in each of the coordinates that end up being 4. So you can see, depending on the choice of the p of the metric, you will end up having different values of your difference. And in other words, by choosing different similarity measure, it will induce different geometry. So different d will induce different geometry. Okay, and keep this in mind because this concept may show up again when we talk about, for example, feature selection later on and lasso algorithm. Okay, so that's the distance is induced by this Minkowski definition. In general, Manhattan distance is also called the Hamming distance when the features are binary. And so it's basically counting the number of entries that are different. And so, for example, you have a 17-dimensional vectors, x and y, as you can see. And so the Hamming distance between these two is going to be 5 as the total number of entries that differ from each other. And in natural language processing, understanding English, and there's something called the added distance. This is the number of addits that has to be made to transform one string into another train of strings. Okay, so for example, this is intention into execution. So you can see how many addits, for example, define deletion as cost 5, substitution is cost 1, insertion as cost 2, and you have to make 1 deletion and then 3 substitution and 1 insertion. The total added distance becomes 10. All right, so you can verify this is a valid distance as well. Okay, so now we have this generalized definition of the similarity measures. We can generalize our k-means. So you can see the only difference now from k-means is, okay, this is the first important difference, let's put it this way, is replace the L2 distance. So before, this is the L2 distance between xi data point from the assigned centroid square. Okay, now we can replace this with the general definition of the similarity measure. Okay, and so based on that, we're going to do similar two-step iterations, very similar to the k-means as before, but this time it's generalized the k-means. We're going to initialize k-cluster centers randomly and decide the cluster memberships of each data points. But this time you can see the assignment is going to be based on this choice of similarity measure, this new d instead of L2 distance. And after that, we're going to solve finding the new centroid through this optimization problem, finding the V. Okay, this V is a new centroid that minimizes the sum of the squared similarities between the V and each of the points that belong to this particular clusters. Okay, and so this is different from before as well, because before in k-means, this d is the L2 distance squared between xi and v. Okay, and so this optimization problem is convex in many scenarios. And so that's going to be a good news. Means it's going to be fairly easy to solve, and there exist computationally efficient methods. And so we start to talk about convex algorithm and convex optimization. And so we'll make the definition formal in the future lectures, as you will see. Okay, so we have generalized the k-means to generalize k-means by replacing the L2 distance to the general definition of D. Now we'll talk about another kind of clustering algorithm called hierarchical clustering. And so the difference of this approach from k-means is that we will organize the data in a hierarchical fashion. And this is also called a dendrogram in many contexts. Okay, and so for example, here we have different strings. These are different names, okay? And we will organize these strings by how similar they are. And so as you can see, we will start to put together the strings that are most similar to each other as one group. So these two pairs, and then we will start to group that, maybe this is another pair that's very similar, and so on. And based on that, in the next level, we will combine the groups that are both similar to each other. And so we end up having a second level. Okay, so the end result of this is you will have this tree structure that tells you how these strings, in this case, each string is one data point, are organized in a tree structure. And based on this, we can perform our clustering because it's very flexible. You could decide to separate the data points at any level of the tree. For example, you say, I decide to cut my tree here, and then that's going to separate your data into two clusters, this and this. And if you decide to cut your tree at this level, as you can see, this is going to form 1, 2, 3, 4, and 5 clusters. Okay, and so the hierarchical clustering is going to give you more information in the sense that you will be able to understand how the data are grouped together in a pretty fine-grained level, and you can zoom in and zoom out sort of by looking at different levels of the tree. And the right-hand side is, I find a pretty interesting example to illustrate how the different countries in EU, in Europe, can be organized in a cluster fashion. Okay, and so here's a description of a hierarchical clustering, and it's also an iterative algorithm. We start with the smallest unit, and so the smallest unit is to say each group only consists of one data points. So to start with, we will have you will have M clusters. Each cluster only contains one data points. And then from there, we're going to start to form the smallest units cluster based on the choice of D. Okay, this D is your similarity measure. And so we will find out the D, given this D, the two clusters that are closest to each other, meaning with the smallest D, and then combine them. Okay, and so once you find the GI and the GJ that are closest to each other, we're going to merge them into a cluster. So these two are the closest to each other, and then we're going to merge them. And then what is the definition of a D? And if you have only one data points, then that's going to be pretty easy to define the D between two clusters. That's going to be the different, D applied on each of the data points, GI and GJ. But if you G contains more than one data points, then this D, Gi, Gj is going to be the smallest D. This is your choice of similarity. The smallest D between X and Y for any X and Y within this group. Okay. All right. So you keep doing this. You keep finding the clusters that are closest to each other and merge them, and then you will form larger and larger clusters. This gives you this hierarchical tree structure until you have finished grouping all the data points. You have constructed this tree. Okay, so here's one example to show you how the hierarchical clustering is performed on that string data. So in this example, for the string purposes, we're gonna assign one value to each of the strings. So Piotr has value 1, Pyotr has value 2, and then Petros have 3.1 value, and Pietro have value 4. And the d, little d between them is going to be the distance between them, okay, the difference between them. And so in the first round, you're going to examine all the cluster. Each cluster only consists of one string, and you can see which two have the smallest distance. And the distance between these two is only 0.9. So that is, you can start either from here or start here. But if I have a certain way of running my algorithm from left to the right, and then you find out these two seems to be the first two cluster you end up having have the smallest distance. So I decided to group these two to form G12. And in the next iteration, I will find out how do we find the smallest distance between these newly formed groups. And you end up finding this one, which has value of 4.9. The difference of this to the two elements in here, the smallest value is 0.9. So this achieves the next smallest distance in your newly formed group. So I decide to merge this group with this newly formed group here. Okay, so keep doing this. In the end, you will end up having this result. Okay, so illustrating how this is performed. Okay, so we have briefly talked about hierarchical clustering and k-means. So what is the difference between the two? Let me write it here briefly. So basically, we talk about k-means and the properties of the k-means algorithm, and then hierarchical clustering. And the k-means typically can work on larger data set. And as we have explained, you can see it's pretty simple alternating between the two steps. Versus the hierarchical clustering typically work with a smaller data set, right? Because you have to do a more bottom-up approach in the hierarchical clustering, because you have to start with each cluster only containing one data point and then start to merge them. And so if you have a very, very large data set, it's going to be very expensive to perform hierarchical clustering. So because of that, k-means is much more popular for large data set. Okay, and so that's it for today's lecture. And also just want to mention that in the homework question, you will see we will talk about a variant of the k-means algorithm. It's called k-modoids, and differences in the k-modoids, the way to assign the centroid is going to be different. Instead of choosing the average as a new centroid, in the k-modoid, it's going to assign pick one of the data point exist in that cluster as a new centroid. Okay, and so you will see this in your homework, and you will also implement the k-means yourself and test its performance on real data set in the homework. Okay, that's it for today.
Okay, here I would like to show a demo of the k-means algorithm. We'll start with the MNIST handwritten digit example. And so first we'll load the data, which is here, and we'll show you what the data look like, and then we start to run the k-means algorithm. Okay, So let's run this code here. Okay, so the first picture here shows the raw data. As you can see, it consists of a bunch of zeros and a bunch of ones. Okay, and this is the result after we perform k-means clustering, and these are the two sets of data points being clustered to each of the clusters. As you can see, this seems to be the cluster for the 0, and this seems to be the cluster for the 1s. It seems like most of the ones are being put into the correct cluster, although there are some zeros like these, because the way they're written, they're like a stroke in this direction, that's being mistaken as a 1 and put in this cluster. And this is a cluster for the zeros. As you can see, these clusters contains mostly 0, although there are some strokes that are because the way they're written seems to be wide and mistaken as 1s. As you can see, the algorithm has tried the best, but it's because of the data is noisy, it's not going to be perfect. And let's see, this is the first demo. Next demo, we want to show you an animation of the process how k-means converge. And this is also a demo code to show you the step of the k-means. And in this example, the data is generated synthetically. There are 6 clusters. The cluster centers and so on are generated randomly as well. And so this is the actual implementation of the k-means. As you can see, alternating between the 2 steps, assign data points to the current cluster, and then finding out the new centroids according to the current assignment, and then alternating between the 2 until there's no change between the center of the current center and the past center. Okay, so you check out the difference between the C in the 2 iterations, and if this is smaller than 10 to minus 6, you're going to stop iteration. Okay, let's see what's going to happen. This is animation, so you can play the code yourself to see the process. As you can see, as it goes, the centroids are being adjusted, and if you look at the points, especially at the boundaries, and the colors are changing, so they are being put into different clusters as iterations go on. Okay, and it's going to converge after a few iterations. Let's check. Here, still running after 24 iterations, and so still making fine tunes. Okay, and finally it converged in 27 iterations. Okay, all right, so that's it. And I would like to say that although here I show the MATLAB demos, but we also provide Python demos, and you're welcome to try that as well. And because in this class we emphasize on the algorithm and the principles behind the algorithm, so I will only explain one programming language to show you how this is implemented, but feel free to explore the Python. I will try to post both versions of demos and for these examples. All right.